Let us now look at the variable and value ordering heuristics. The backtracking algorithm contains a call to select the unassigned variable, and it simply selects the next unassigned variable in the order given by the list of variables. Now, this static ordering would seldom result in efficient search. Therefore, the idea is to choose variables with the fewest legal values. Let us try to understand this with the help of our map coloring example. So, on your right, we have the map coloring problem with 7 variables. Let us say after the assignment of WA to red, we assign NT as green. Now, there is only one value possible for SA here, and that is blue. So, it makes sense to assign blue here rather than assigning the value for Q. This is what the minimum remaining value heuristic does. Now, it has also been called the most constrained variable or the fail fast heuristic, because it picks up a variable that is most likely to cause a failure soon, thereby pruning the search tree. The minimum remaining value heuristic does not help at all in choosing what would be the first region to color in our map coloring problem, because all of these 7 variables when we start can be colored in any one of red, blue or green. Now, this is where the degree heuristic comes in handy. The degree heuristic lets us to choose a variable with the most constraints on remaining variables, and it does attempts to reduce the branching factor by choosing the variable that is involved in the largest number of constraints on other unassigned variables. For the map coloring problem, if you look at the 7 variables, SA is the variable with the highest degree, which is 1, 2, 3, 4 and 5. The other variables have degree either 2 or 3, except TA here, which has a degree 0. So, we choose the variable with the most constraints on the remaining variable, that is, we first choose SA and thereafter we choose NT and so on and so forth. Applying the degree heuristic actually solves the problem without any false step. If we keep on choosing the consistent color at each choice point, we can still arrive at a solution with no backtracking. These 2 heuristics that we have discussed actually we are looking at which variable to select, but then once a variable is selected, the algorithm must decide on the order in which to examine the values of the variable. This is where the least constraining value heuristic comes into play. The least constraining value heuristic allows us to choose the variable that rules out the fewest values in the remaining variables. Coming back to our map coloring example, let us see that after a partial assignment of red and green to WA and NT respectively, what is our choice for Q? We could now choose to color Q either blue or red, but we need to understand that blue is a bad choice, because it would then eliminate the only legal value possible for SA. So, the least constraining value heuristic prefers to color Q red rather than coloring it blue. So far our search algorithms that we have considered, the constraints on them only looked at the variable when it is chosen. It would be a good idea to look at some of the constraints earlier in the search or even before the search has started. This can then drastically reduce the search space. Let us look at one such idea called the forward checking. The forward checking keeps track of the remaining legal values for any unassigned variable, and then it terminates search if any value has no legal values to color from. So let us look at this map coloring example to understand forward checking. Here on your right is the constraint graph, and we have 7 variables as we have been discussing. To start with, all these variables could be colored in any one of the 3 colors. Now let us say that we have colored WA red. When WA is colored red, then the variable NT and the variable SA, the only legal colors left for them is green, blue. And now if we color Q as green, then the only legal values left for NT and SA is blue, whereas NS could be colored red and blue. After we have now decided to color V as blue, we see that we are left with no legal colors for SA, and the search must thus terminate. The forward check propagates information but does not provide early detection for all failures, as we will see when we look at this newer idea of constraint propagation. Constraint propagation propagates the implications of a constraint onto the variable, other variables, to detect inconsistency. So continuing with our map coloring example, we initially have all 3 colors for each of the 7 variables. Now after we color WA red, the only legal values left for NT and SA is green and blue. At that point, if we color Q green, the legal values that's possible for NT and SA is blue, but because we are propagating this information locally from one variable onto other variables, we now immediately realize that NT and SA cannot both be blue together, and therefore we know we will not be left with a solution, a path to a solution, if we carry forward our coloring this way. So constraint propagation repeatedly enforces constraints locally and could detect failure early. We will look at a cryptic arithmetic puzzle in order to do this. So here is a puzzle which says send plus more is equal to money. As I had told you earlier, I could think of placeholders for S, E, and D, and I could have placeholders for M, O, R, and E, on which I will put my guess of digits between 0 and 9, and then I would have placeholders for M, O, N, E, and Y. And then, as discussed earlier, we have carryovers 1, 2, 3, and 4, which we call C1, C2, C3, and C4. And we create a placeholder table where the guess for M, O, S, R, Y, D, E, N the 3 plus 3, 6, 7, 8 variables that I have to identify is to be recorded. Now, the first thing that I must realize in this problem to be solved as constraint satisfaction is that here only search will not give me a solution. I have to do some reasoning along with the search, and when I am doing this, I have to think of taking the constraints forward. When I am making a guess, I make a guess and then take this constraint forward and see if it violates or conflicts. If it violates or conflicts, then I should come back and do a search again for another value for that variable. So, to start with, we should realize that here C4 should be 1, because the carryover can be either 1 or 0, but a crypto-arithmetic puzzle requires that the first placeholder is not a 0, therefore C4 must be 1, and in that case I have m equal to 1. So, my first answer of getting to a constraint being satisfied is the fact that the constraint between C4 and m gives me an answer that m is equal to 1. Given m is equal to 1, I update my table by putting 1 here and putting 1 again in a place where m is occurring. So, I put a 1 there, and next I focus on looking for an answer to either the second column or the third column. So, if I focus on the second column, I could see that I have a constraint between C3, S and O. M already is known to me to be 1, and it is required that I have to carry forward a 1. So, the number here would be 10 or something more than 10. So, my initial guess could be that let that be a 0. That means O is a 0 in the sense that this is 10. So, I start with O being 0 and take O equal to 0 and put zeros in these placeholders 0 and 0. Given O equal to 0, I then have a interesting relationship that I need to understand. Third column here, I have E here and I have N here, and this is a 0, and we should realize that E plus N, there must be some relation. The En is a pair, and I should realize that N cannot be 0 even if En is a pair, because already 0 is taken by O, and the En pair, for E to be different than N, C2 must be at least 1. Otherwise, if C2 is 0, E plus 0 is actually E. So, E and N will be the same number. That gives me a very interesting realization that the carry forward C2 is 1. Once I realize the carry forward C2 is 1, I then take one step further and assume C3 to be 0. Once I take C3 to be 0, I have then S plus 1 is equal to 10, because that is a carryover. So, S plus 1 is equal to 10 gives me S is equal to 9. So, I have my third variable satisfied, S equal to 9. I update my variables, S equal to 9 there, and then now I have to look for R, E, N, D and Y. So, I focus on my fourth column and I realize that N plus R must be E plus 10, because I need to carry over 1 there. So, this value that I get in my fourth column must not be E alone, but E plus 10, then only I can carry over C2. So, I write that N plus R is equal to 10 plus E, and already from here my third column I know the fact that E plus 1 is equal to n. Given these two, I can substitute E plus 1 for n here, and then I will have r equal to 9. But the moment I have r equal to 9, I realize that s is already 9, so there is a conflict. At that point of time, C1 comes to my rescue. So I say C1 is actually not 0 but 1. If C1 is 1, then I have C1 plus n plus r is equal to 10 plus e. So this one is like plus 1 here. 1 plus n plus r is equal to 10 plus e. In that case, r will come out as 8, and it does not have a conflict. So I update this C1 as 1, and I realize r is 8. So put my 8 value there. Now it is interesting to note that I have a relation between E and n already there as a pair, but my last column also makes it clear that there is a relation between D and E. But only thing that I must realize is that the y that I have is actually the relationship that D plus E is equal to 10 plus y, because I have a carry of 1 here. So once we look at this, then I know that D plus E is 10 plus y, but we know that y cannot be 0 because 0 is already taken by O here. So D plus E is not equal to 10, neither is D plus E equal to 11, because if D plus E is equal to 11, y is equal to 1, but we already know m is equal to 1, so there would be a conflict. So the only possibility at this point of time is that D plus E is equal to 12. If D plus E is equal to 12, then y is equal to 2. With y equal to 2, I already have a carry over 1, so that is pretty good. So this is what I populate my placeholder with, y equal to 2. So now all I have is to find out the values for D, E and n. Now it is interesting to note that I know E plus 1 is n, and from here I know that D plus E is 12. D plus E could be 12 for digits 0 to 9 in a number of ways. One could be that I could start with D equal to 3, but if I start with D equal to 3, I would have E equal to 9, but S is already 9, so D equal to 3 is not a possibility. Then I could start with D equal to 4, but if I take D equal to 4, E would be equal to 8, in which case it would conflict with R equal to 8, so D is not 4. Then I start with D equal to 5. I could see that if I take D equal to 5, I will have E equal to 7. This is satisfied, no conflict. But then let me check what happens if I have E equal to 7. E equal to 7 would mean that n is equal to 8, in which case it will conflict with R. Therefore, I have a realization that actually D is not 5 but 7, and I have D equal to 7, in which case E is equal to 5 and n is equal to 6. So I could populate these numbers there, and now I have all the variables satisfied, none of the constraints violated, and if you add them now, I have 7 plus 5 12, 2 carry over 1, 6 plus 1 7 plus 8 15, 5 carry over 1, 5 plus 1 6, and then 9 plus 1 10, 0 carry over 1 and 1. So this is the solution for the crypto arithmetic puzzle, sand plus more equal to money, with these values for the different letters. What one needs to understand here is that when this puzzle was being solved, we had done search and reasoning intermingled. It is not that I was only searching and trying to satisfy constraints. Searching was done to satisfy constraints, but also what was being done was that I was doing some amount of reasoning to understand what should be my next guess. So these type of things is what is usually done in constraint propagation. Constraint propagation is the general term for propagating the implications of a constraint on one variable onto other variables, and we want to do this fast. So it's no good if I want to reduce the amount of search, but if we spend more time propagating constraints than we would have spent doing a simple search, there is no point of propagating the constraint. So we want to have very fast propagation of constraints. A very fast method of constraint propagation that is substantially stronger than the forward checking that we have discussed today is arc consistency. Let us now try to understand the idea of how arc consistency provides a fast method of constraint propagation that is substantially stronger than forward checking. So here an arc refers to a directed arc in the constraint graph. An arc x to y is consistent if for every value Vx of x there is some value Vy for y. So let us say in our example of the map coloring, the current domains of SA and NSW are blue and red blue respectively. Given the current domains of SA and NSW, we could see that there is a consistent assignment for SA equal to blue. I could always pick up NSW equal to red, and I can therefore have a consistent assignment from SA to NSW. Whereas if I am looking for arc consistency from NSW to SA, if I pick up red, I could have a legal value blue here, but if I pick up blue, I do not have a legal value in SA. Therefore, the arc from SA to NSW is consistent, whereas NSW to SA is not. All that the arc consistency tells me is that I have a consistent arc from SA to NSW. Arc consistency can be used as a look ahead to search for space reduction, and the idea is in two ways. Either we look for full arc consistency look ahead, or we look for directed arc consistency look ahead. The full arc consistency look ahead is about considering all pairs of future variables and then removing values from one domain for which a consistent value in the other domain does not exist. The directional arc consistency look ahead is about considering only directional arc for the future variable. Like in the example that we were discussing for the map coloring problem, SA to NSW, the arc is a directional arc consistency. Arcs that become inconsistent could be made consistent by deleting the inconsistent values. Like if here we think of making arc consistency, we can think of deleting certain value from NSW, that is the value blue, and we would end up having consistency from NSW to SA. But the problem is, if I delete a value from some variable's domain, a new inconsistency could arise in arcs pointing to that variable. So arc consistency must be applied repeatedly until no more inconsistencies remain. This is what we will try to understand in this example here. So on your right is the constraint graph, Let us assume the current domains that we have for the different variables NT, SA, V and NSW as shown. So, as you can see, there is consistency from SA to NSW, because for a value from SA I can pick up a value from NSW, but the other way it is not correct. So, I can delete the blue value, and then what I will have is a consistent arc between NSW and SA. But then if we have realized this, earlier the arc between V and NSW was consistent, but because of deletion of blue, if I now pick up red this side, I will have inconsistency, because I will have no legal value for NSW available. And therefore, to maintain arc consistency, I need to delete red from here. And then I have enforced arc consistency between NSW and V one more time. This has to be applied repeatedly until I have no more inconsistencies in the constraint graph. Now, if you look at these two domains of NT and SA, if I somehow apply arc consistency between them, then I would need to delete blue from NT in order to have arc consistency between SA and NT. So, enforcing arc consistency from the arc from NT to SA would make the domain of NT empty. And this is how arc consistency could detect failures earlier than forward checking.